Welcome. I am about to embark on a derivative review, a review of how to take derivatives. And this is your professor, Dr. Gallenstein. Okay, so what I want to do in this video, in this review, is first go through the basic formula of derivatives, some rules, and then to do some examples, just take some examples. So let's start with the basic formula. If I have a function, and let's say my function equals x, let's say it equals a times x to the b power, then the derivative of that function is equal to b times a times x to the b minus 1 power. Here's your basic formula. So when you run into a derivative problem, you want to be able to fit it into this formula. There's going to be a couple exceptions that I'll get to in just a minute. But let's look at some examples. So let's say I have f of x and it equals to 2x to the third power. If I look at my general formula, I can say, oh, that 2 is the a, the 3 is the b. So then let's just use the formula. The a, so what is it? It's b times a. Okay, that means 3 times 2 times x to the b minus 1. Well, 3 is b, so 3 minus 1 is 2. So there we go. We notice that 3 times 2 is equal to 6, so we have 6x squared. Now, one other kind of simple way of thinking about it is that I take the exponent, I multiply it. So I kind of do this in one step, and I just think, oh, okay, 3 times 2 equals 6x, and then 3 minus 1 is 2. So I just kind of do this we can do this really quickly. Now, there's some examples of this kind of simple approach that aren't immediately obvious, so let me use another example. What if I had f of x equals 5? What is the derivative of f of x with respect to x of the number 5? Well, to understand this, in terms of our formula, we need to just be reminded of a simple property, and that is that x raised to the 0 power is equal to 1. And so what we can look here, and we can say that this f equals 5 is actually the same thing as saying f equals 5 times x to the 0. But because x to the 0 is just 1, x isn't there. So we can think about this equation in this way, that 5 equals x to the 0 power. And if that's the case, then we can use our formula and figure this out more quickly. So if x is raised to the 0 power, let's use our formula. So 0 is b, so then it's b, 0, times a. A, of course, is the 5. And then we have x to the 0 minus 1 power. Now we look at this and we say, wait a second, any number multiplied by 0 is just 0. So then this equals 0. Which means, if we think about this just very simply, if I ever take a derivative of a function, let's say I have a function of x, and it doesn't have x in it. So it's just some number. It could be any number. It could be 10, or I could have f of x equals y, or you name it. Any term that doesn't have the variable to which, with respect to which you are taking the derivative, that term is just going to be 0. So the derivative of this with respect to x is equal to 0. The derivative of this with respect to x is equal to 0. So on. Okay, let's do another quick example. Let's say f of x is equal to the square root of x. We look at this, one thing we're going to do is we're just going to think, oh wait, now the square root of x is the same thing as x to the 1/2. Now once I convert it over to x equals x to the 1/2, this becomes a lot simpler to calculate, because it's, oh, okay, let's just apply my formula. The derivative of f of x with respect to x equals 1/2 x. You subtract 1, right? So it's 1/2 minus 1. 1/2 minus 1 is minus 1/2. So that's what this equals to. Now, if I use my exponent principles, I can say that any number or any variable x raised to a negative exponent is the same thing as 1 over that variable raised to the positive exponent. So 1 over x to the 1/2. Sorry that that's a little small and hard to see, but this is 1/2 here, if you're following me. And like we know, x to the 1/2 is the square root of x. So this could be 1/2 times 1 over square root of x. And then we'll just simply combine this and simplify it. So it'll be 1 over 2 square root of x. So the derivative of f of x with respect to x is 1 over 2 square root of x. Okay, so that's kind of the simple, formula, the basic formula. So let's look at some rules that will allow us to accommodate some more complicated situations. So let's look at some rules. First, let's look at the addition rule. Okay. So let's say I have a function f of x, and it equals some function g of x plus some other function h of x. The derivative of f of x with respect to x is equal to the derivative of g with respect to x plus the derivative of h with respect to x. So basically you just take the derivative of these two separate kind of sub-functions, if you will. So let's do a simple example. Let's say that f of x equals 2x squared plus 3x to the 4th. The derivative of f of x over x equals, first the derivative of this term, so it's 2 times 2 is 4, x, 2 minus 1 is 1, so it's just 4x. All right? 4 times, then the derivative of this term, so 4 times 3 is 12, x, 4 minus 1 is 3, 3. There we go. That's the addition rule. Let's think of another quick example. Let's say I have a plus b times x plus x to the b plus ax cubed. Try to make it a little more complicated. Derivative of x with respect to x, this would equal, so I can treat this whole addition term as basically as my a in the original kind of equation. So this is just becomes a plus b. All right, so the derivative of this term becomes a plus b plus here we just bring the b down, b times x, b minus 1, basic formula, plus we bring the 3 down, so 3 times a, x to the 2, x squared. Okay, so that's my derivative there. Okay, I'm going to go to the next page. All right, our next one, we're going to do the product rule. The product rule, let's say I have a function f of x, and f of x equals some function g of x times some function h of x. The derivative of f of x with respect to x is equal to the derivative of g of x times h of x plus g of x times the derivative of h of x. And just making a quick note here, I'm using this shorthand notation. The derivative of g of x with respect to x, I'm using just a different notation for that, g prime of x. It's a little bit simpler to write this. I'll use this prime notation when I have a function of only one variable, and so it's obvious what it is I'm taking the function with respect to. If it only has one variable, then there's only one thing with respect to which I can take the derivative, and so I can just use the prime because a reader reading this would know that the derivative is with respect to x. I'll make that more clear a little bit later. Okay, so this is the product rule. Let's do an example. Let's say f of x equals, let's say I have x squared times 2 minus x. Let's just say I have that. When I look at this, I can say, oh, wait. This is kind of its own sub-function, if you will. So let me call that g of x. And I look at this, and this is kind of its own sub-function, if you will. So let's call this h of x. I can apply the product rule. So let me do that. Derivative of f of x with respect to x. First, derivative of g of x with respect to x, that's 2x times h of x, so 2 minus x, plus g of x, so that's x squared, times the derivative of h of x, which I look in here and I see that that's negative 1. Then I can go on to simplify that. Let's distribute this. It becomes 4x minus 2x squared minus x squared. And I can simplify this out. So 4x minus 3x x squared. Okay. So there is an example. Okay. Let's go to the next one, the quotient rule. The quotient rule is one of the most complicated. The quotient rule. So let's say I have some function f of x, and it equals some function g of x divided by some function h of x. In this case, the derivative of f of x with respect to x is equal to the derivative, using the shorthand notation again here, the derivative of g of x times h of x minus g of x times h prime of x divided by h of x squared. Kind of a big complicated equation, but it can be quite helpful. So let's look at an example. A very simple example would be f of x equals 1 over x. Now, as an aside, this becomes easier. I can just say that f of x equals x to the minus 1. Take the derivative of f of x with respect to x, and I get minus 1 times x to the minus 2, which we know is negative 1 over x squared. So that's if we want to avoid the quotient rule, sometimes you can take the thing on the bottom and bring it up to the top and use your negative exponent rule. So this is a simpler way of solving this problem than the quotient rule. But sometimes you'll want to use the quotient rule, sometimes you'll want to use this. So I just illustrate there as an aside. Okay, but let's apply the quotient rule in this case, just for completeness sake. All right, derivative with respect to x. So what is g of x? Well, g of x is just 1. What is h of x? Well, it's x. So what's the derivative of g of x? So just following our formula, the derivative of g of x is 0. And multiply that by h of x, which is x, minus g of x, which is 1, times the derivative of minus the derivative of h of x, which is just 1, divided by h of x squared, which is x squared. When we simplify this, we see, okay, 0 times x is just 0. Negative 1 times 1 is just negative 1. And so we get 1 over x squared, and so we confirm our result. We confirm our result. Now, you're more likely to use the quotient rule when you're facing a much more complicated function. So let's think of an example of a function. Let's say we have 2x cubed divided by x squared minus 5. We can see that my g of x here equals 2x cubed. My h of x here equals x squared minus 5. So then let's apply the quotient rule. Derivative of f of x with respect to x is, okay, we use our rule, so the derivative of g is 6x squared times h of x, which is x squared minus 5, minus g of x times the derivative of h of x, which is 2x, divided by h of x squared. So there we go. And we can simplify this further if we would like. So let's just simplify it. Let's distribute this on top. So it's going to be 6x to the 4th minus 5 times 6 is 30x squared. Then we're going to come here, minus 4x to the 4th over, and we don't necessarily need to expand the bottom. This is pretty clean, so let's leave that there. And then we'll simplify it by saying 2x to the 4th minus 30x squared over x squared minus 5 squared. Okay, so there's my derivative. All right, so that's quotient rule. Okay. All right, and let's do the chain rule. Chain rule is very important. It comes up all the time. It comes up when we take total derivatives. So we use this rule a lot. It's very important. If I have a function f of x and it equals some function g of another function h of x, then I need to use the chain rule. The derivative of f of x with respect to x is equal to the derivative of g with h of x plugged into it still times the derivative of h. So when we're doing economics, let's say we have a utility function. Our utility function is a function of x, but x is a function of some parameter alpha. If we have this and I say, how does alpha affect my utility? I need to use the chain rule. So I would need to take the derivative of u with respect to alpha is going to be equal to the derivative of u with respect to x times the derivative of x with respect to alpha. This is an application of the chain rule. The outer function, g, is now the utility function. The inner function, h, is now x. And x is now alpha. So we have to apply the chain rule. You take the derivative of the outer function times the derivative of the inner function. Okay, I'm going to re-articulate this in another way to make sure that it's clear. So let me write this again. So I have g as a function of h as a function of x. The derivative of f of x with respect to x is equal to the derivative of g with respect to h of x times, let's write this, the derivative of h of x with respect to x. So let me just rewrite that. Now this will parallel here a little bit more clearly. Another way of thinking about this that sometimes can be helpful is we can see, okay, I have function f of x is of g of h of x. Let me just call h of x mu for the moment. Let me just call it that. I'm just going to substitute it out. So g equals mu. So then the chain rule would imply this. The derivative of g with respect to mu times the derivative of mu with respect to x. Just to help make that a little bit more clear. Hopefully it's more clear. Okay, so let's do an example of the chain rule. And then we'll look at a total derivative where we use the chain rule, and we'll see why it's important and how it applies. So let's do some examples. Let's say I have some function f of x equals, let's say x squared plus 10x minus 5 squared. That's my function. When I see that, I think, okay, g, my function g of h of x, the g function is this squared function. So let's say I just replaced h of x with some generic letter like I did before, mu. So then it's g of mu equals mu squared. So it's this outer function. The g function is this outer function, this squared function. H of x is equal to this, x squared plus 10x minus 5. So if we want to apply the chain rule, first we take the derivative of the outer function, that's the squared function, right? So what do? We take the derivative of f of x with respect to x equals the derivative of the outer function, g of h of x, take the derivative with respect to h of x, times the derivative of h of x with respect to x. So what is that? What's this term? Here, it would be 2 times x squared plus 10x minus 5. Because this, remember, this term here is h of x. So you take the derivative of g of x with respect to h of x. So you have 2 times the inside function. And you multiply that by the derivative of h of x. So let's put this in a parentheses. What's the derivative of this? Well, we go term by term. 2 times x plus 10. So there is my derivative using the chain rule. Let's take a look at another example. Let's say f of x equals square root of, let's see, square root of x cubed plus, let's just say 2x. Okay, so here, what we're going to recognize here is that my outer function g of x, is this square root function, so raised to the 1/2. So then when I go to take the derivative, I'm going to convert this into the different notation of 1/2 and bring the 1/2 down. So it's going to be 1/2 times my h of x, right? I should clarify that. H of x is equal to the x cubed plus 2x. All right, so it's h of x inside, raised to the negative 1/2, times the derivative of h of x, which is 3x squared plus 2. I can simplify this and say 1 over 2 times the square root of x cubed plus 2x times 3x squared plus 2, which is going to be equal to 3x2 plus 2, or 3x squared plus 2, over 2 x cubed plus 2x. Okay, so that would be my derivative using the chain rule. Okay, so let's look at a total derivative. Okay, total derivative. So let's say we have a function, and it's a function of x and alpha, okay? But x itself is also a function of alpha. So this is our function. And I want to take the derivative of this with respect to alpha. Derivative of f with respect to alpha. A total derivative, what you do is you use the chain rule for all of the variables that are functions of the parameter to which you are the parameter with respect to which you are taking the derivative. So you do that, you take the chain rules for all the variables that are themselves functions, and then you take the derivative with respect to the parameter itself. So if I want to do this, what I'm going to do is I'm going to have the derivative of f with respect to x times the derivative of x with respect to alpha. This is just the chain rule. I use the chain rule because f is a function of x, but x is a function of alpha. So if I want to take the derivative with respect to alpha, I need to use the chain rule. I need to take the derivative of f with respect to x times the derivative of x with respect to alpha. This is the chain rule. So I need to use this. But then plus what's called the direct derivative. So it's just the derivative of the function with respect to alpha, ignoring the fact that x is a function of alpha. So it's just the derivative of f with respect to alpha. And this is my total derivative. If I have a function, let's say I have a function of x, which is itself a function of alpha, and y, which is itself a function of alpha, and alpha, and I want to know what's the derivative of f with respect to alpha, what I'm going to do is I'm going to take multiple chain rules. The derivative of f with respect to x times the derivative of x with respect to alpha plus the derivative of f with respect to y times the derivative of y with respect to alpha plus the derivative of f with respect to alpha. So here I'm using the chain rule. And then this term is called the direct derivative. Okay. Now the total derivative, we use the total derivative usually, almost exclusively, when we have some function that isn't defined. And so usually when we're taking the total derivative, this is literally what we're writing. We're writing out all of these derivative notations rather than actually taking the derivative of a function that we know. So doing an example of the total derivative is not necessarily helpful because we don't really take total derivatives of functions that are defined. But let me illustrate that by doing so. Let me give an example of a total derivative, and I hope that my example here will illustrate my point. So let's say we have this function f. The function is a function of x, which is itself a function of alpha, and then f is also directly a function of alpha. Well, let me write out what a function could be. Let's say this function is 4 times x plus alpha squared. Okay, if I want to take the total derivative of this function with respect to alpha, when I look at this function, I'm going to think, at first glance, I might be tempted to just say that the derivative is 2 alpha. But remember the way I specified this. X is itself actually a function of alpha. So that means I need to do more than one thing here. I need to take the derivative of this function with respect to x. I need to use the chain rule, basically. So let me apply the chain rule first. What's the derivative of the function with respect to x? Well, that's 4. But x is a function of alpha, so using the chain rule, I need the derivative of x with respect to alpha. This is my chain rule term. If we go back to our example, we have a chain rule term where we have the derivative of the function with respect to x times the derivative of x with respect to alpha. So that's what we've just done here. Now we need our direct derivative. The direct derivative is 2 alpha. So this is my total derivative with respect to alpha. But you'll recognize that we still have this term here, this derivative of x with respect to alpha. Why do we have that? Well, the reason that we have that is I haven't told you what x of alpha is. I haven't told you what it is. So it's still a generic function. I haven't told you what the function is. A function, x of alpha, is going to be some equation, some term that has alpha in it. So let me come down here and specify what x of alpha is. Let's say x of alpha is alpha over 2. So this function, x of alpha, is equal to alpha over 2. Okay, well let's plug that into the total derivative and see what we come up with. So we have f of x to the f of x, where x is a function of alpha. We know that this is 4x plus